Hi, this is Gangadhar from Grad Government College, Nizamabad. So, lecture in mathematics. So, today topic is BSc third year in the linear algebra. Orthogonal sets, orthonormal sets, and orthogonal projection. So, first orthogonal definition. So, what is the definition of orthogonal? Means u comma we are two vectors in the vector space V over F. If inner product of u dot v equal to 0, inner product of u dot v equal to 0, then u comma v are called orthogonal vectors. Inner product of u comma v equal to 0, then we say that u comma v are called orthogonal vectors. So now the definition of orthogonal set means in a set each pair of distinct vectors inner product is 0, then that set is called a orthogonal set. Means a set of vectors u1 u2 so on up in R to the power n is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. That is, if ui dot uj equals 0 if I is not equal to j or whenever I is not equal to j. So ui dot uj equals 0 whenever I is not equal to j means two different vectors inner product is 0. So in the given set each pair of distinct vectors are orthogonal, then given set is called orthogonal set. So now the example, see the example. Show that u1, u2, u3 is an orthogonal set where u1 equal to 3, 1, 1, u2 equal to minus 1, 2, 1, u3 equal to minus 1 by 2, minus 2, 7 by 2. So now we show that given set is orthogonal set. Means each pair of distinct vectors inner product is 0, then we say that given set is orthogonal set. So we find the inner product of u1 u2 comma u1 u3 and u2 u3. So first we find inner product of u1 u2, that is u1 dot u2 equal to u1 transpose into u2, 3 into minus 1 plus 1 into 2 plus 1 into 1. So minus 3 plus 2 plus 1 equal to 0. So first one u1 dot u2 equal to 0. So now second one u1 dot u3. So u1 dot u3 means u1 transpose into u3, 3 into minus 1 by 2 plus 1 into minus 2 plus 1 into 7 by 2. So minus 3 by 2 minus 2 plus 7 by 2. So result value 0. So u1 dot u3 also 0 here. So next u2 dot u3. So u2 dot u3 equal to u2 transpose into u3 means minus 1 into minus 1 by 2 plus 2 into minus 2 plus 1 into 7 by 2. So we get result value is 0. So therefore we get u1 dot u2 0, u1 dot u3 0, u2 dot u3 also 0. So we say that u1, u2, u3 are orthogonal vectors and these vectors form orthogonal set. So we say that given set is a orthogonal set. So next problem, which of the following vectors are orthogonals? So here three vectors are given. So we check given vectors are orthogonal or not. So first two vectors. So minus 1, 4, minus 3, 5, 2, 1, 3, minus 4, minus 7. So 3 vectors are given. So we say that these 3 vectors are v1, v2, v3. So here we find v1 dot v2, v2 dot v3, v3 dot v1 values. So if these 3 inner products are 0, then we say that given vectors are orthogonal vectors. So now first v1 dot v2, its definition: v1 transpose into v2, v1 transpose into v2 means minus 1 into 5 plus 4 into 2 plus minus 3 into 1 equal to minus 5 plus 8 minus 3 equal to 0. So we get v1 dot v2 equal to 0. Next v2 dot v3. So v2 dot v3 equal to v2 transpose into v3. 5 into 3 plus 2 into minus 4 plus 1 into minus 7, that equal to 15 minus 4 minus 7. 15 minus 11, result value 4, not equal to 0. So v2 dot v3 value not equal to 0, means these two are not orthogonal vectors. Next v3 dot v1. So v3 dot v1 equal to v3 transpose into v1. So 3 into minus 1 plus minus 4 into 4 plus minus 7 into minus 3, that equal to minus 3 minus 16 plus 21 equal to 2, not equal 0. So v2 dot v3 not equal 0 and v3 dot v1 also not equal 0. Means given set is not orthogonal set. Next problem. So 1 minus 2 1, 0 1 2, minus 5 minus 2 1. 3 vectors are given. Say v1 comma v2 comma v3. First v1 dot v2. So v1 dot v2 value we get 0. Same way v1 dot v3, that value also we get 0. Next v2 dot v3. So 0 1 2 into minus 5 minus 2 1, 0 into minus 5 plus 1 into minus 2 plus 2 into 1. So 0 minus 2 plus 2 equal to 0. So here inner product of two distinct vectors is 0. Means given vectors are orthogonal vectors and their forming set is called orthogonal set. So therefore there are 3 pair of vectors in the set are orthogonal. So and the given set is called orthogonal set. So next problem. 3 minus 2 1 3 one vector, minus 1 3 minus 3 4 another vector, third vector 3 8 7 0. So we say that UVW3 vectors. First u dot v value. So u dot v value we get 0. 3 into minus 1 plus minus 2 into 3 plus 1 into minus 3 plus 3 into 4 equal to 0. Next u dot w, 3 into 3 plus minus 2 into 8 plus 1 into 7 plus 3 into 0. So that value also we get 0. 9 minus 16 plus 7, that equal to 0. Next v dot w, second vector, third vector, minus 1 into 3 plus 3 into 8 minus 3 into 7 plus 4 into 0. So minus 3 plus 24 minus 21, that equal to 24 minus 24 equal to 0. So each pair of vectors inner product is 0. So we say that given 3 vectors form orthogonal set. Next one problem. So 5 minus 4 0 3 one vector, minus 4 1 minus 3 8 another vector, 3 3 5 minus 1 one vector. So here first u dot to be, so u dot to be value 5 into minus 4 plus minus 4 into 1 plus 0 into minus 3 plus 3 into 8, that value we get 0. Next u dot w, that value also we get 0. Next v dot w, minus 4 1 minus 3 8 3 3 5 minus 1. So this inner product value also we get minus 32, means not equal 0. So u dot to be inner product 0, u dot w inner product 0, v dot w inner product minus 32 not equal to 0, means so these two v and w vectors are not orthogonal. So we say that given vectors set is not orthogonal set. So here we have one theorem. So the theorem statement, if S equal to u1 u2 so on up is an orthogonal set of non-zero vectors in R to the power n, then S is linear independent and hence is a basis for the subspace spanned by S. So S is orthogonal set of non-zero vectors and then S is linear independent and hence it is basis set also. So first linear independent set. So linear independent set means we show that in the linear combination of the set vectors we equate to 0 bar, and in that linear combination using all scalar values are 0, then we say that given set is linear independent. So first we write linear combination of elements of given set and we equate that linear combination 0 bar, and we show that in that linear combination using scalar values are zeros, all scalar values are zeros, or that equation has trivial solution, then we say that given set is linear independent set. So now first we will take linear combination of elements of the given set C1 U1 plus C2 U2 plus so on plus CP UP equal to we say 0 bar. So that equal to 0 bar. So 0 equal to we write 0 equal to we write 0 into 0 bar into U1, 0 bar equal to we write 0 bar into U1 also. So here we write 0 bar value. What is 0 bar value? C1 U1 plus so on plus C2 U2 plus so on plus CP UP. So now that equal to C1 U1 plus C2 U2 plus so on plus CP UP into U1. So that equal to C1 U1 dot U1 plus C2 U2 dot U1 plus so on plus CP UP dot U1. So now C1 into U1 dot U1 plus C2 into U2 dot U1 plus so on plus CP into UP dot U1. So but here S is orthogonal set. S is orthogonal set means what is the definition of orthogonal set? In the set S, every pair of two distinct vectors inner product is 0. So every pair of two distinct vectors are orthogonal vectors. Each pair of two distinct vectors are orthogonal vectors. Means u2 dot u1 0 and so on up dot u1 also 0. So orthogonal set means inner product of two distinct vectors is 0. Inner product of two distinct vectors is 0. So orthogonal set. So u2 dot u1 0. So on up dot u1 also 0. Then 0 bar equal to we get c1 into u1 dot u1. But here u1 dot u1 is a vector. It is a non-zero vector. So and u1 is orthogonal to. So u1 dot u1 into c1 equal to 0. Means c1 value we get 0. u1 dot u1 not equal 0. So c1 equal to 0. c1 equal to 0 means same way, suppose into u2 we will take, then we get c2 0 into un cp into up is we will take 0 equal to 0 into u1 plus u1 plus we write u2 u3 so on up, then we get c1 c2 so on cp values are zeros. If c1 c2 so on cp values are zeros, then we say that S equal to u1 u2 so on up is linear independent set, and the set form basis for the subspace spanned by S. So now the definition of orthogonal basis. Orthogonal basis. So an orthogonal basis for a subspace W of r to the power n is a subspace for W that is also an orthogonal set. So orthogonal set is basis for the vector space. Basis for the vector space, then it is called orthogonal basis. Orthogonal set is basis for the vector space, then we say that it is orthogonal basis. So let u1 u2 so on up be an orthogonal basis for a subspace W of r to the power n. For each y in W that waits in the linear combination, that is, so y equal to c1 u1 plus so on plus cp up. So means, so here u1 u2 so on up be an orthogonal basis for subspace of W of r to the power n, and y is in W, then y is linear combination of u1 u2 so on up, that is y equal to c1 u1 plus c2 u2 plus so on plus cp up. So and cj equal to definition y dot uj by uj dot uj, j equal to 1 to so on p. So one problem. So the problem is the set u1 u2 so on u3 is an orthogonal basis of R3. Express the vector y equal to 6 1 minus 8 as linear combination of the vectors in S. So S equal to given u1 u2 u3 values, u1 equal to 3 1 1, u2 equal to minus 1 2 1, u3 equal to minus 1 by 2 minus 2 7 by 2. So we show that y is a linear combination of elements of S, means y equal to we write to c1 u1 plus c2 u2 plus c3 u3, and c1 in that linear combination scalars c1 c2 c3 values are exist, then we say that y is a linear combination of the elements of S. So now here first we find the values. Direct linear combination definition is there. The definition y equal to y dot u1 by u1 dot u1 into u1 plus y dot u2 by u2 dot u2 into u2 plus y dot u3 by u3 dot u3 into u3. So we find y dot u1, y dot u2, y dot u3, and u1 dot u1, u2 dot u2, u3 dot u3. So y dot u1 equal to 11, y dot u2 equal to minus 12, y dot u3 equal to minus 33. Next u1 dot u1 equal to 11, u2 dot u2 equal to 6, u3 dot u3 equal to 33 by 2. Direct linear combination definition, y equal to y dot u1 by u1 dot u1 into u1 plus y dot u2 by u2 dot u2 into u2 plus y dot u3 by u3 dot u3 into u3. So we know the values y dot u1, u1 dot u1, y dot u2, u2 dot u2, y dot u3, u3 dot u3. These values we substitute in this linear combination. Then we get the linear combination is y equal to u1 minus 2u2 minus 2u3. So it is the required linear combination. So same model problem. Show that u1 u2 or u1 u2 u3 is an orthogonal basis for r2 or r3 respectively. Then express x is linear combination of u's. So we write x is linear combination of u1 u2. So directly we know the formula. So linear combination of x equal to x dot u1 by u1 dot u1 into u1 plus x dot u2 by u2 dot u2 into u2. Direct linear combination. So first we find x dot u1 equal to the value 39, u1 dot u1 equal to 13. Next x dot u2 equal to 26, u2 dot u2 equal to 52. So x equal to, we substitute the values, then we get the linear combination 3u1 plus 1 by 2 u2. It is the linear combination value of x. Same model, next problem u1 101, u2 minus 141, u3 321 minus 2, and x value 8 minus 4 minus 3. X value 8 minus 4 minus 3. So first we find the value u1 dot u1, u2 dot u2, u3 dot u3. u1 dot u1, u2 dot u2, u3 dot u3. So u1 dot u1, u1 dot u2. So inner product is 0. Same way u1 dot u3, inner product is 0. u2 dot u3, inner product is 0. So we say that these three inner product values are zeros, means given set is orthogonal set. Given set is orthogonal set. So they are orthogonal. So given set is orthogonal. Put these vectors in matrix and reduce it to echelon form. So three vectors we write in matrix and that matrix is reduced to echelon form. So in the echelon form, so 3 2 1 0 0 18 and 0 minus 1 4. So it is so here diagonal values are 3 minus 1 18. 3 minus 1 18 values are diagonal values. So here we have 3 pivot columns. 3 pivot columns. First column, second column, third column also pivot columns. 3 pivot columns. 3 vectors are there, means these 3 vectors are linear independent vectors and these vectors form basis for the R3. So now we write x is the linear combination of the vectors. X equal to alpha u1 plus beta u2 plus gamma u3, and we write in matrix form Ax equal to b. In the Ax equal to b, so box AB augmented matrix that augmented matrix is reduced to upper triangular form, and again we write the equations. Those equations are solved for the given variables. So we get the values are equations 18 gamma 18 gamma equal to 6, we get gamma equal to 1 by 3. Next, minus beta plus 4 gamma equal to 1, from that we get beta value 1 by 3. Next, 3 alpha plus 2 beta plus gamma equal to 5. So here we substitute gamma and beta values, then we get alpha value 4 by 3. So now x is the alpha into v1 plus beta into v2 plus gamma into v3. We write alpha, beta, gamma values. So it is the linear combination required. So next one definition is orthogonal projection. So orthogonal projection definition is, so given let u be non-zero vector in R to the power n, so u is non-zero vector in R to the power n. Consider the problem of decomposition of a vector y in R to the power n into the sum of two vectors, one a multiple of u and the other orthogonal to u. So we wish to write y equal to y complement plus z, y equal to y complement plus z. So here, if z is orthogonal to u, if and only if, so the alpha value y dot u by u dot u and y complement equal to y dot u by u dot u. Y complement equal to y dot u by u dot u is called orthogonal projection of y onto u. Orthogonal projection of y onto u. So here u is one vector in R to the power n and y also another vector in R to the power n. Then y dot u by u dot u into u is called orthogonal projection of y onto u. So here y equal to, we write y complement plus z in that. So y complement is orthogonal projection and z is called orthogonal to u. Z is called the component of y orthogonal to u. So y equal to y complement z, in that y complement is called orthogonal projection of y onto u, and the vector z is called the component of y orthogonal to u. Component of y orthogonal to u. So projection of y on u definition formula, it is denoted by y complement equal to projection y on L equal to y dot u by u dot u, y dot u by u dot u into u. So it is orthogonal projection of y on u. So now problem. Let y equal to 7, 6, u equal to 4, 2. Find the orthogonal projection of y onto u. Then write y as sum of two orthogonal vectors, one in span u and one in orthogonal to u. So first, orthogonal projection of y on u is y complement equal to formula, y complement equal to y dot u by u dot u into u. We find the y dot u value 40, u dot u value 20, and projection of y on u is y complement equal to y dot u by u dot u into u, that equal to 2 into 4 2 matrix, we get 8 4 8 4. the orthogonal projection of y onto u is y complement equal to 8, 4. Next, find the component of y orthogonal to u, that is z value. Y minus y complement. Y minus y complement is component of y on orthogonal to u, z value. Y minus y complement. So that value we get minus 1, 2. So now the sum of these two vectors is y. So y equal to y cap y complement or y cap plus z. Y equal to y cap plus z. So now, so we show that orthogonal projection y and z values orthogonals. So y complement into y minus y complement into z equal to 0. So y complement y cap into y minus y complement y cap equal to 8, 4 into minus 1, 2 value we get 0. So now the problem here. So compute the orthogonal projection of 1, 7 onto the line through minus 4, 2 and the origin. So projection of 1, 7 means it is the y value onto the line through minus 4, 2 at the origin means u value minus 4, 2. So orthogonal projection formula y cap equal to y dot u by u dot u into u. So 1, 7 first y dot u value 1, 7 into minus 4, 2, that equal to minus 4 plus 14 equal to we get 10. Next u dot u minus 4 comma 2 dot minus 4 comma 2, 16 plus 4, 20. So y cap orthogonal projection of y on u is y cap equal to y dot u by u dot u into u. So 10 by 20 into u value minus 4, 2 matrix, that equal to vector minus 2, 1. So same way next problem. So here the vectors 1 minus 1 y value minus 1, 3 u value. So we want y dot u value first minus 4. Next to u dot u value we get 10. So y cap equal to y dot u by u dot u into u. So it is orthogonal projection of y on u. So we get 2 by 5 minus 6 by 5. So here the problem, another one, let y equal to 2, 3 and u equal to 4 minus 7. Write y as the sum of two orthogonal vectors, one in span u and one in orthogonal to u. So now first we find orthogonal projection of y on u, y cap equal to y dot u by u dot u into u. So y dot u value minus 13, u dot u value 65, y cap value minus 4 by 5, 7 by 5. So first we write y cap is the part that is in the span u. So y minus y cap equal to z, component of y is, it is. So z value 4 by 5, 8 by 5. And we write y equal to y cap plus z, y cap plus z, y equal to. So it is the linear combination. So orthonormal set. So now the definition is orthonormal set. First, orthogonal set definition. Orthogonals is u dot v equal to 0, inner product of two vectors u dot v equal to 0. Then we say that u comma v are orthogonals. Orthogonal set definition is, so in the set each pair of distinct vectors are orthogonals, then that set is called orthogonal set. So now here orthogonal orthonormal set. Orthonormal set. So a set U1, U2, so on UP is an orthonormal set if it is an orthogonal set of unit vectors. So orthogonal set of unit vectors. If W is the subspace spanned by such a set, then U1, U2, so on UP is an orthonormal basis for W. So first the set U1, U2, so on UP is orthogonal set with unit vectors. Orthogonal set of unit vectors. And this set is basis, then we say that it is orthonormal basis for W. So now orthonormal set means same vectors inner product is 1, different vectors inner product is 0. Then given set is called orthonormal. Same vectors inner product is 1 and different vectors inner product is 0. Then we say that given set is orthonormal set, and that set is basis for the given vector space, so it is called orthonormal basis. So now here we see the problem. So one set is given, show that v1, v2, v3 is an orthonormal basis of R3. Orthonormal basis means same vectors inner product is 1 and different vectors inner product is 0. Then we say that given set is orthonormal basis. So v1, v2, v3, three vectors are given. So we find inner product of v1, v2, different vectors. We show that here different vectors inner product is 0. v1, v2 inner product, we multiply these two, v1 into v2, we get the result value 0. Next v1, v3 inner product, v1 transpose into v3, that value we get 0. Next inner product of v2, v3, also 0. So now different vectors inner product is 0 here. Next we find same vectors inner product, that is v1 dot v1. v1 dot v1 equal to v1 transpose into v1 or square root of direct we find 1 we get. v2 dot v2 1, v3 dot v3 1. So here different vectors inner product is 0 and same vectors inner product is 1. So therefore we say that given vectors set is called orthonormal set. If the set is linear independent, then it is called a orthonormal basis for R3. So now one note. So an M by N matrix U has orthonormal columns if and only if U transpose into U equal to I. So U transpose into U equal to I, then we say that U is unitary matrix. So let U be M by N matrix with orthonormal columns and x comma y be in R to the power n, then norm ux equal to x, norm ux equal to norm x. Next ux dot uy equal to x dot y, ux dot uy equal to x dot y. Third one, ux dot uy equal to 0 if and only if x dot y equal to 0. So here we have an example. So a problem is, let u equal to 1 by root 2 column 1 by root 2 1 by root 2 0, second column 2 by 3 minus 2 by 3 1 by 3, and x vector is given root 2 3. So u has orthonormal columns and u transpose into u value is I here. U transpose into u value is I, unit vector. So verify that norm ux equal to norm x, norm ux equal to norm x. First we find u into x value. U into x value means So 1 by root 2, 2 by 3, 1 by root 2 minus 2 by 3, 0, 1 by 3 into root 2, 3. So result value we get 3 minus 1, 1. Result value we get 3 minus 1, 1. It is the ux value. So but here we want norm ux. So norm ux equal to square root of 3 square plus minus 1 whole square plus 1 square, that is root 11. So next norm x value root 2 whole square plus 3 square. So 2 plus 9 root 11. So here therefore LHS is equal to RHS, norm ux equal to norm x. Next problem. So determine which set of vectors are orthonormal. If a set is only orthogonal, normalize the vectors to produce an orthonormal set. So here two vectors are given. So 1 by 3, 1 by 3, 1 by 3 minus 1 by 2, 0, 1 by 2. So first we verify given two vectors are orthogonal or not. So we find u dot v value. U dot v value 1 by 3 into minus 1 by 2 plus 1 by 3 into 0 plus 1 by 3 into 1 by 2. 0 we get. U dot v equals 0 means u comma v are orthogonal vectors. Next we find same vectors inner product, u dot u value and v dot v value. So u dot u equal to 1 by 3 we get, v dot v equal to we get 1 by 2. Not equal to 1. So u dot v is 0, but u dot u and v dot v value not equal to 1 means u comma v is not orthonormal set. U comma v is not orthonormal set. So here we find unit vector of u and which vectors are from orthonormal basis. Orthonormal basis means here we find a normal unit normal vector of u and v. Unit normal vector of u and v. So unit normal vector of unit vector of u is u by norm u and unit vector of v is v by norm v. So we find u by norm u value and v by norm v value also. So these two unit vectors of u and v form orthonormal set. So same one problem is given. So three vectors are given. Show that those three vectors are orthonormal basis or not. So inner product of same vectors, different vectors, u dot v inner product 0, u dot w inner products 0, v dot w inner products also 0. So different vectors inner product is 0 here. Next we want same vectors inner product, we get u dot u1, v dot v1, w dot w also get 1. So same vectors inner product is 1 and different vectors inner product is 0. So therefore given set of vectors is orthonormal set. Thank you.